Now let's look at three different methods to improve coverage and capacity. Number one is what we call cell splitting, which results in increasing the number of base stations. Number two, sectoring, antenna directions adjustment to reduce co-channel interference. And number three, zone microcell, antenna power adjustment to reduce co-channel interference. We'll take them in details. So let's take one at a time. Cell splitting. Cell splitting, as you can see in the following diagram, the idea is to subdivide congested cells into smaller cells, which we call microcells. Each of them will have its own base station. Of course, to do this, we need either reduction in antenna height and reduction in antenna power, one or both of them. So let's say that these cells are congested, so we can have microcells, smaller cells in size, and now we have to have additional base stations. We'll have microcells, and each of them will have its own base station. So, and each of them will have different frequency according to the frequency planning to reduce the interference. Now the capacity is increased because the frequency reuse factor is now improved. Capacity is increased by increasing the number of times the channel frequency is being reused, and more clusters, of course, for the same service area. We have to worry about the interference. In cell splitting, we're showing now a practical example, and it states the following. Both R and D are reduced at the same rate, so Q is not changed. Signal to interference ratio is not changed. Depending on the new design cell radius, the transmitted power should be readjusted such that the power received at the new cell boundary should equal to the power received at the old cell boundary, because we had big cell, now we are reducing it by using microcells. So you can see the bold lines show the original cells, and microcells create smaller cells. So power reduction is expected to be there. And since PR is proportional to PT times the radius raised to power minus n, then the reduction in power, if the reduction of the cell is reduced by alpha r, so we have, let's say, half of the original radius or quarter, then the transmitted power should be reduced by a factor which is alpha raised to power n. So the ratio between the two should be between the original transmitted power with before microcell splitting and after should be alpha raised to power n. So if alpha is 0.5, n is equal to 2, we need 1/4, because n is a path loss and we have changed the distance, so it's a function of n and alpha. Now, as we mentioned, if r is reduced by half, then n equal to 4, then it's going to be a reduction of power of 16. If n was 2, then we get 1/4. It's just direct substitution into the following expression. How much capacity enhancement is achieved by cell splitting? How much did we gain by doing this? For reducing the radius by half, we are reducing cell area by 1/4, multiplying the number of clusters in the service area by 4. Remember that area is proportional to the square. So if the radius is half, then we have a factor of 4. Therefore, the capacity number of the channels is quadrupled. Is now quadrupled, multiplied by 4. At what cost? Either increasing the number of base stations by a factor of 4, and at the same time, of course, more handoff sophisticated, and which requires, of course, sophisticated and advanced processing. Remember that different cell size systems, not all cells have or need to be splitted. In this case, different cell sizes exist, different transmitters, different powers, which complicate the system. So let's say that this is the system. Let's say that this is only in the square where we start having cell splitting. Channel assignments become, of course, complicated because we don't have exactly the same size. So this is one issue with cell splitting. The second solution to improve coverage and capacity is sectoring. So what's sectoring? In every cell, we're going to divide the cell into sectors. So let's say the base station in the middle here, this example of 3 sectors, and this example of 6 sectors. So we're going to use directional antennas. So one antenna pointing to every direction. And common examples include radiation pattern or sectoring patterns of 120 degrees. So the 360 here will be divided into 120. We need 3 directional antenna. This is very common. We can also have 60 degrees sectoring, where we have 6 antennas and they are going to cover 60 degrees each. The channel assigned to a cell, of course, will be divided over the sectors. So if I have 60 channels, for example, then we'll have 20 channels per sector here, or 10 channels per sector here. So sectoring can be done by using directional antenna. We reduce, of course, the main objective is to reduce the number of co-channel interference. So let's say that we have number 5 here, surrounded by each. This guy now is going to interfere only with cells in the same direction. The opposite directions will not cause interference. For 120 degrees sectoring, the first tier interference would be reduced from 6 to only 2. For example, this 5 will include only 2 in the first tier. Of course, they will have others in the second tier. But what's important is the first tier, the first circle. So the reduction is by 1/3. Now, if you do the signal to interference ratio, remember the equation before we had? The simple equation? Then instead of dividing by 6, we are now dividing by 2. The improvement in terms of power, okay, is 3 times, or in log scale, 10 log base 10 of 3, that would give you 5 dB. If you use the better approximation that we had before, you will find out that the reduction, the improvement would be 6.4 dB instead, which is a good amount of improvement. Okay, so we can translate this improvement into a reduction in N, which implies, of course, more clusters. Either reduce the interference, or you keep the same interference level and reduce N, which of course results into more clusters or more number of uses of the same frequency. Of course, if you don't do sectorings, the equation is what you have seen here. So just to recall. So here is showing you the 2 scenarios with omnidirectional interference. 6 distinct interferers. We'd have A, and all around. And on this case, you'll find that because of the directional antenna, you're going, for example, this P would include this P and that P only. All these 1, 2, 3 would be dropped out. All right. Let's do the following example. With sectoring. Let's say that the objective is to achieve a signal to interference ratio of 21 dB, assuming path loss exponent, that's N, equal to 4. Let's compare the 2 scenarios with sectoring and without sectoring. So the simplified equation we use, we have 2 equations here. I colored N here with different colors just to distinguish. So for the case of no sectorings, we're going to divide by 6. And we have the signal to noise ratio. We'll convert that into the linear scale and we'll solve for N. Can you find the answer? Just try to pause the video and find the answer. Now, I'll just set the answer now. The answer is N equal to 12. The smallest cluster size is N equal to 12. Of course, if you go higher than this, you'll get less signal to interference ratio. Now, for the case of the 120 degree sectorings, we'll use this equation instead. And if we solve for N, you try it yourself. You can pause the video now. I'm going to set the answer. The answer is N equal to 7. that means we have an increase in capacity, almost double, in fact to be more exact 12/7, using this simplified equation. So the advantage of sectoring is pretty clear. Now let's try to understand how much capacity enhancement is there by sectoring. Remember the following equation on the right, which says that a simple way of measuring the signal to interference ratio will depend on path loss and the number of interfering cells. We have seen that this is approximately, we got a gain of 6.4 dB. Now, let's assume that n equal to 4, that's small n equal to 4, for the case of path loss, n equal to 4, we can reduce n by a factor of square root of 10.64, which is 2.09. How did we get this? Take two scenarios and compare them together. So this is a linear scale, 6.4. How do you get the linear scale? You divide by 10 and 10 raised to the power that. So you get 10 raised to the power 0.64. That's the signal to interference ratio. So that's the signal to, let me just try to mark this. So this guy here, okay, is this guy here. Now we have n, small n equal to 4, and square root here we'll get 3. Of course we'll get 3 raised to the power 2 because of 4. And now if you compare two scenarios, the 3 and the I will cancel out, and then you will be solving for the improvement in n, which becomes a square root of 10.64, which is 2.09. That's an improvement of a factor of 2. But you know, you have to be careful because we don't pick any number for n. We cannot take 8, so we have the closest is we go from 7 to 4. We have reduced n by a factor of 4. So we have enhanced the capacity, the number of channels, by a factor of 1.75. 1.75 is 7 divided by 4. But you have to be careful because what we enhanced is the number of channels. What we have enhanced is the number of channels, but not the number of users. Why? Because of the following. Now, when we have changed n, the number of channels per cell is increased due to the smaller value of n, and the 3 sectors will divide the cell's channels among them. So not all the channels will go onto the cells because of sectorings. These channels will be divided. All right, and the number of channels per sector is less than the number of channels in a cell before sectorization. So there is a reduction in the number of cells, number of channels per sector. This results in a decrease in the trunking efficiency, which leads, of course, to lowering the number of subscribers to keep the same grade of service. So sectoring is reduced interference, but at the price of less efficiency in utilizing the number of users. So we need to trade off things. Let's take an example to understand this last comment. Let's take an example to understand the trade-off between number of channels and number of users. So given number of available voice channels is 400, small n path loss exponent is 4, capital N number of cells per cluster is 7, the traffic per user is 0.03 Erlang. We require a grade of service of 0.01. What is the capacity improvement in terms of number of channels and number of users? Now, when we do the unsectored design, the number of channels per cell, all right, so we have 400 divided by 7. Don't worry about the control now. So we have 57 channels per cell. For a grade of service of 1% blocking, that's we use Erlang B curves. We go to that curve because we're looking at blocking Erlang B formulas or curves, and that will give you A equal to 44.2 Erlangs. Okay, and now of course, if every user is taking 0.03 Erlang, then you divide the total traffic by the traffic per user. That will give you 1,473 users. For the case of sector design, we'll get n equal to 4. Okay, that will result in improvement, reducing the interference. And now instead of using n equal to 7, we can use n equal to 4. So let's repeat the analysis. Number of channels per cell is now 100. So it increased from 57 to 100. However, the number of channels per sector now is 33. Okay, this 33 is less than the original number of cells in the entire number of channels in the entire sector. So although it increased here, but now with sectoring it's now reduced again, and this reduction is less than the original one. So for a grade of service of 1%, you'll find out that with this number of channels you'll get 22 Erlang. That's from the Erlang B curves. I advise you to stop the video and go back to the slides, find out the 22. The number of users per sectors is now 733. The number of users per sector is now 733, and of course per cell is now we have 2199. So in general there is an improvement, but per sector you have to be careful when you calculate when you do the calculation per sector. So the capacity enhancement in terms of number of users is 2199 divided by 1473, which is 1.5 and not 1.75. Okay, so this is not all translate into capacity increase enhancement in users. So this is the number of channels, but now we have 1.5 for the number of users. While capacity in terms of number of channels is 1.75, as I just mentioned. Note that in this example, the sector system still provide marginal improvement in signal to interference ratio over the unsectored system. So there is improvement when it comes to comparing sectors. Of course, you have to take into account the hardware, the cost of the antennas and installation and processing required as a result. If we decide to utilize sectorization for the sole purpose of increased signal to interference ratio, then the sectored system will result in reduction in number of subscribers. So one thing, you can trade off the signal to interference ratio increase and the number of users. Now let's summarize the cell sectoring pros and cons. So the first, let's start with the advantages. We'll mention two. Improve the signal to interference ratio of the system. We get a gain of about 7 dB is achieved over omnidirectional antennas, omnidirectional systems where there is no sectoring, when a 20-degree sectoring is used. When it comes to the problems or cons, we have increased handoff requirement from one sector to another, because when the user moves from one sector to another, he needs to be handed over. Multiple antennas are required in a base station, hardware cost, processing cost. Decreased trunking efficiency, because if we don't have all the channels, if the number of channels per sector is now less, we have less trunking efficiency. The third solution to improving the capacity and the coverage is what we call the microcell zone concept. The microcell zone concept is like this. The high power single transmitter, which covers the area, is replaced with 3 lower power transmitters. So this is the area we would like to cover. We replace it with 1, 2, 3 transmitters. Each transmitter defines a microcell. All microcell transmitters are connected to the base station via fiber optics or coaxial or microwave, so they are all connected together to the base station. A mobile in a cell is served by one zone at any instant of time. So this guy is served by the red circle. As he moves, he will be covered by one of the sectors. Cell channels are in pool of all zones, but there's no sub-trunking, and this is the key idea. So we're not dividing the frequency zones into different sectors. All of them are covered by one big zone, and there's no sub-trunking. Once a channel is assigned to a zone, it's not assigned to any other zone. So if it's used here, it's not going to be assigned here, so there is no interference. A mobile user travels from one zone to another, and the system will retain his frequency. because we have one big control here. If this car moves to the next zone, it will retain its frequency. Handoff is not required by the mobile switching center when we cross the zone, but of course it's because it's handled by the same base station. So the same frequency will be used without changing because all of the zones are controlled by the base station. So this is a solution that is kind of trade-off, which maintains the advantage of sectoring, the advantage of dividing into cells while retaining the channels, because there is no sub-trunking. Antennas are spaced, but they are all connected to the base station. Now we can ask the question, why capacity enhancement is achieved by microcell zone? First, because a frequency is used in one zone only, part of the cell, at any instant of time, at a lower power. The co-channel interference is generally reduced. There is no co-channel interference as before because we have lower power and it's used by only one zone. To say it in a different way, put it differently, for the same signal to interference ratio of the normal system, we can have smaller cluster size or more frequency reuse, leading to increased capacity. Unlike sectoring, no sub-trunking is done within the cell, therefore the gain from reducing the cluster size is intact. So microcell is different than sectoring. Now let's demonstrate the concept of microcell, the microcell zone. Let's say that the minimum required signal to interference ratio is 18 dB. And we would like to use the concept of microcells now. Instead of using a radius r from here to here and distance d from here to here, we'd like to use the concept of microcell zone. So consider a 7-cell structure, and this is the equation. This is the more accurate equation to find the signal to interference ratio. So what is Q here? It's D divided by R. D divided by R, you can find it's going to be 4.6. To maintain this 4.6, by substituting, you can substitute 18 dB here by converting into linear scale. That's going to be 10 raised to power 1.8, and solve for Q. That Q is going to be 4.6. But we know also that Q is D over R. Now, if we want to go to have a microcell, then instead of R, okay, to the edge, we'll have RZ from here to here. So this big cell, now we have microcell shown in circles, 3 microcells. Now, if we want to maintain the same signal to interference ratio, so now D sub Z, R sub Z, which is in the new small zone, the microcell, should be maintained as 4.6. Now, let's try to approximate things with circles. So the hexagonal is represented with a circle. Then we can say that approximately from here to here, compared from here to here, or this is the radius. While let me just highlight this with this is R from here to here, and this is RZ. So we can think that RZ will be half of the original radius, assuming we are looking at circles. Now DZ, with a little bit of calculation, the distance between the adjacent co-channels now we're comparing. Let me just highlight again with colors. This is the original D from here to here, and I would like to compare with this new D. So we can say now that that's going to be 4 over 3 with simple geometric approximation. So it's becoming 3 over 4. Now if you look at the ratio dz over rz, it's going to be, if you divide these two together, this side of the equation, we will get that this is going to, the 4 with the 2 would give you 2, so this is going to be approximately equal to 3, right? So d over, if you solve for, we know that if you solve here for d over r from these two equations, you'll find that d over r should equal to 3 approximately. I'll leave this for you to show, but it's straightforward from these two equations. Now q, which is equal to d over r, and we know for hexagonal square root of 3n will get you n equal to 3, which means now we have reduced the requirement from 7 up to 3 with cell macrozone. So the channel expansion is 7/3, and the user expansion is also 7/3. The reason for maintaining the channel expansion and user expansion is that there is no sub-trunking here. Now, the cost, of course, because in engineering usually we get something, we lose something. So the cost, of course, is smarter base stations and the need for connection. So the construction of the microcell itself will have to be done in a smarter way, which is more costly. Now I'll leave it for you as an exercise in the comment section. Please repeat the analysis with different dB scale. Let's say 24 dB is the requirement, and show us how much you get in terms of numbers and what is the channel expansion. Thank you. We'll see you in coming videos.